Hello, everybody. So this is going to be the lecture two for week six, I think. And what we're going to be going over is solving systems of equations. So in the week six page, you'll find the week six lecture two PDF. You can download that. I've already got it open right here. And so this is going to be demonstrating what we can do with linear systems of equations in MATLAB. So I'm going to open up Octave, actually. Octave, there we go. And we'll get started. So what folder am I in? Let us let us try to fix this. So my interface is a little bit messed up. So let me go Window. Let's try to reset the window layout. There we go. Better. And let me change into a better folder. There we go. And now we can get going. So um, what we want to talk about is representing systems as matrices, right? So we know that MATLAB is good at dealing with matrices, and we know that you can represent a system of equations as matrices, right? Because we've already done this before, although we did it in a very simplistic way where we input a system of equations as a matrix. And then what we did was we tried to do row operations on that, just I don't know, just to try to learn how to deal with matrices, basically. We weren't really getting much accomplished. But you can represent a system of equations as matrices, right? So if you have a system of equations like this, here's an example, 3x plus 2y equals 18, negative x plus 2y equals 2, and you want to solve it, like how would you do it, right? There are a lot of online solvers, and in fact, I will show you one. So if we go here, and looks like I closed it, but if we say, what do I want? Something, I don't know, systems of equations like this. And you'll see, I mean, this is not Google, but you'll see that the top links are Wolfram Alpha and Symbolab, right? So Symbolab is one of the ones that people like, and Wolfram Alpha is also one of the ones that people like. So I'll just click on Symbolab here, and it says System of Equations Examples, and you can click on one of the examples to see how to type it in. And you can see that it looks like they just type in the equations and they have just separated by commas, right? So if we wanted to do the ones we have here, right, 3x plus 2y equals 18, you would just say 3x plus 2y equals 18, comma, and then the other one is negative x plus 2y equals 2. So negative x plus 2y equals 2. Didn't type it in successfully. Negative x plus 2y equals 2. And then I should be able to say go, and it should tell me the answer, and it shows us how to do it, right? So you can solve by substitution, and it'll give you directions, right? You could solve the first equation for x, then you could substitute that x into the second equation, and then you can simplify that, and eventually you can find that x equals 4. And then once you have x equals 4, then you can substitute that into the other equation, and you can find y. That's one way to do it. You could also plot them and find out that they intersect at 4, 3. That's another way to do it. And this exists here, right? Like there are ways to solve this. So um, how would we do it in MATLAB though? That's the question. And so you separate this out into, well, first of all, you have to write it in the right form. So you need it the way it's written here with the variables all on the left side and the constant on the other side, right? So 3x plus 2y equals 18. So we would not want the 18 on the left-hand side. We would want it separated out on the right-hand side. And same for the other equation. Okay. And then you have 3x plus 2y, and you have negative x plus 2y. And so the coefficients, what we call the coefficient matrix, would be you have a 3, you have a 2. So the top row would be 3 comma 2. And then for the second equation, you have negative x, so the coefficient negative 1. and 2 for the y. So you have -1 and 2. So you type in what we call the coefficient matrix. That's the A. So you go over here and you say A equals whatever we had, 3, 2. So you go 3, 2, semicolon, and then the second row is -1, +2. So -1, +2. We'll hit enter, and there we go. So we have 3, 2, -1, 2, right? 3, 2, -1, 2. So that's the coefficient matrix. That's the A that they're talking about here. Now, when you type AX equals B, the X is not the X variable, it's the X vector. So I don't really have a place to type that right now. Maybe you can type it in my notes. Um, so you can think of it like this. So the vector X is actually X and Y. So, the reason they use X is because you could, for your variables, you don't have to use X and Y. Your variables could be like X1, X2. If you have more variables, X3, X4, et cetera, right? However many variables you have. So the unknowns are your X's. And so for us, the X vector is X, Y. Now, technically, it's a column vector. So I'll show you this in class when we get to class on Thursday. But the A is that 2 by 2 matrix. The X is the column XY. And then the B is also a column, and that column is the constants that we put on the other side. So that's why it was important to put the constants on the right-hand side. If you don't, then the signs will be wrong for your constants. So constants go on the right, and we have an 18 and we have a 2. So you put that like this. So it'll be a column. So you can use a semicolon. That's one way to type it. Let's go over here. So you can type it X equals, I already forgot what it was, 18 and 2. So you can type it in 18 semicolon 2, and you'll get a column like that. Or you could type it in as 18, 2, and then you put an apostrophe on the outside, and that apostrophe is the transpose operator, which we learned changes rows to columns and columns to rows. So you do that, and you'll get a column vector just like that. Okay, so this is what happens. So we have now two matrices, right? Technically, we have the A and we have the B, and you can think of both of those as matrices. And so what we want to do is we want to try to solve this equation up here, AX equals B, to get the X vector, the X vector being X and Y. So in linear algebra, this is a little bit awkward, but there's a matrix called A inverse, which I just typed this way because it was what I could do in the slides. And the matrix A inverse has the property that A times A inverse equals the identity, which I wrote 1 here, but that's not really correct. It should be I. Now, just to show you that, I'll come over here to Octave. And so this is the matrix A that we typed in. If I wanted the inverse in Octave or MATLAB, you would type INV for inverse A. And then this would be the inverse. And so it's just another matrix. It's going to be the same size as the original matrix, and it's just going to have different numbers. But the properties that it has is that if you take the matrix A and you multiply it by the inverse of A, you get what we call the identity matrix, which this is the identity matrix, 1, 0, 0, 1. And so that special property lets us solve equations, because if we go back here, if you had an equation AX equals B as it's written here, then if you wanted to solve this for X, what you would do is you would multiply both sides by A inverse. And the result will be this. X equals inverse A times B. And so this right here is one way that you could actually solve the entire system of equations in MATLAB. So just to illustrate that, let's go back here. So we typed in A, it was this. We typed in B, it was this. So 2 by 2, and then this is a 2 by 1. And if you multiply the inverse of A times B, this is your answer. So you could say X equals inverse of A times B. And we'll get 4, 3. So the X is 4 and the Y is 3. And of course, that should be exactly what Symbolab came up with. X equals 4, Y equals 3. And that's what you would get by hand. But there's even a shorthand notation for that in MATLAB. Like this is so common that instead of doing inverse A times B, they just say A backslash B. And you get 4 comma 3. So that's actually really, really simple, right? So it lets you solve systems of equations in MATLAB in a very easy way to do that. I'll probably post another video where I kind of do some of this by hand to kind of illustrate some of the terminology for you. But for the moment, this is pretty straightforward, right? So wait, why is this? I don't know what happened here. Did this get typed in wrong? 3, 2, negative 1, 2. 3, 2, negative 1, 2. Oh, okay. This one's typed in wrong. So this is back to the example, but this is not the example, right? The example was 18.2. Oh yeah, the example was 18.2, but it looks like I typed in the B wrong. I typed in negative 1. So technically this slide is incorrect because I solved the wrong system of equations, but we were just trying to solve the system, right? So what it looks from beginning to end is actually very quick. So let's say we've done nothing and we wanted to solve this system of equations. You'd say A equals, and then you would type in the coefficient matrix. So you go square brackets. You go 3, 2. So you go 3, 2, semicolon, negative 1, 2. So negative 1, 2. There you go. I always leave the semicolon off the end um, so I could look at it and just make sure I typed it in correctly. And then B equals, and we need to type it as a column. So that's 18.2 apostrophe. That's how I'll type it. And then to solve it, you just do X equals A backslash B. So X equals A backslash B, 4 comma 3. So the answer is 4 comma 3. It's not this. This is the solution if you had a negative 1 there for the B, which was incorrect. I typed it wrong. So we solved a system, right? And that's kind of it, more or less. You want to make sure a couple of things. So make sure that you type your B as a column. You could look at it after you type it in just to make sure that it's correct. But there's a few ways that you could do it, right? So one way is to use the semicolon, like 1 semicolon 2. The semicolon kind of means go down to the next row. So this is 1, go down to the next row, 2. So this is okay. You could type it in as a row, 1, 2, and then put an apostrophe. The apostrophe does the transpose, makes it a column. You could type it 1, comma 2, and then with an apostrophe. 1, comma 2 is also a row. So a apostrophe on the outside does the transpose and makes it a column. But if you type 1, comma 2 with no apostrophe, that's a row, and that's wrong. If you type 1 or 1, 2, no apostrophe, that's also not okay. And so if you type it in wrong, right? So if I type B equals, it should have been 18 anyway, 18.2, and then you try to do A backslash B, you're going to get an error. And so the error is going to tell you that basically these are the wrong size. And so you have to make sure you go back, fix the B to make it a column, and then A backslash B would just give you your answer right away. And so the point that I'm trying to illustrate here is that it's actually very quick to solve systems of equations in MATLAB because MATLAB is really good at dealing with matrices. And that operation that formally happens where you find this matrix A inverse, that's a slow operation generally, but MATLAB is very good at it. And so if your matrices are not super big, then it's going to be pretty dang quick. Now, how quick is going to depend on your computer and also like what kind of libraries you have in there. Like just to show you, I can go back here. I can make a random matrix. So like if you do like rand 3, for example, you get a random 3 by 3 matrix. Um, Generally, that will be invertible. Um, so like you could do something like this. I could say um, A equals, um, what do I want? Rand, like you could say 100, right? That would be a random 100 by 100 matrix. I put a semicolon because we don't want to see it, but you can see it's 100 by 100 here. And then you could say inverse A, and it still was able to convert. Well, we didn't see it, but it was able to compute the inverse of A in, a moment. Now, if you make the matrices really big, it's going to be slower. Um, like if we go, let's say, make it 1,000, y inverse A. Oh man. Well, this is why you put semicolons on the end of things. Did we do 1,000? So 1,000 by 1,000 is 1,000,000 entries. So we're waiting for 1,000,000 entries to scroll by. I don't know how many we've seen. There's no way to know. I'll just let it go though. Do do do. I think every time we see that flashy thing, we're getting onto the next row, maybe. I'm just going to hit Control C and stop it. That's not right. Okay. So anyway, should have had a semicolon, and then it still happens basically instantly. We were only waiting for it to scroll. So if you do a 10,000 by 10,000, that's a very big matrix. And if I do the inverse now this is not instant, right? So 1,000 by 1,000, it was very quick, but for a 10,000 by 10,000, it was not quick. By the way, something we haven't talked about, but we can, is there's a built-in function in MATLAB and Octave called like tick tock. And so there's this command called tick. And when you do it, it doesn't look like it does anything. But what it actually did was it started a timer. And if you want to stop the timer, you type toc, T-O-C. So T-I-C, T-O-C, tick tock. And when you type toc and hit return, then it tells you how long it was between the tick and the toc. And so what you could do is you could actually build a line that looks something like this. So I could say um, like A equals, let's make a random 5,000 by 5,000 matrix. I'm going to press semicolon, but I'm not going to go down to the next line. I'm going to start a clock, tick. Then I'm going to find the inverse A, semicolon. And then when we're done, I'm going to do a toc. So I can type this all in one line. So it's going to create a random 5,000 by 5,000 matrix, start a clock, find the inverse of the matrix, and stop the clock. And that way we'll see how long it took to invert the matrix. So if I hit enter now, took 1.5 seconds. And so I could run that as many times as I want. Um, it generally will speed up if you do it several times in a row. Sometimes the first time's a little slow, but you can see there's going to be some variance here because my computer is doing other things. And also, by default, we're probably not using all of my CPUs. Like this, I think, is a 16-core processor, but we're not using all 16 cores here. We're probably only just using one core. Um, and so this is going to be quite slow compared to how fast it could be. Um, but this is fast enough. You could change things to see how long it takes. Like if we go from 5,000 to 6,000, how long does that take? We see that this was about a second and a half. If I do ran 6,000, it's going to be slower. You can see it actually going from 5,000 to 6,000 actually makes it go from like 1.5 seconds to like 2.5 seconds. Um, ish, right? We don't really know because I only ran it one time. We go to 7,000. Oh, now it's like 3.6 seconds. So you can see that as the matrices get bigger and bigger, the inverse is slower and slower to calculate. And that's basically all of the time that it takes. So like when you're doing this operation, multiplying the matrix times the b is very, very quick. So actually computing the matrix, that's the entire slow time. In fact, we can even do that. We can figure it out. So let's do this one more time. So this is a 7,000 by 7,000. And you can see it's also 3.6 seconds. So if I wanted to add like a system of equations, I can do a random. I can do b equals random. And in order to match up with the 7,000, I would need 7,000 rows, one column. Um, and then instead of doing inverse A, we can do inverse A times B. So that's like solving the system of equations. We can even put x equals there. So this should be about the same amount of time. Uh, let's try it again. What happened here? Oh, comma, we want semicolon. All right, try again. So it was about 3.6 seconds before, right? And you can see it still is 3.6 seconds. So actually like adding the b here, the times b did not slow this down at all. In fact, somehow it seems faster. Oh, well now it's slow. Um, so it's about 3.6 seconds, but there's obviously you can see that it varies. Um, cool. Also, if you do the other method of solving, a backslash b, that might be faster. When you do a backslash b, it knows that it's solving a system of equations and it can sometimes apply optimizations to the process. So you can see that it's actually significantly faster. And that's just because this x equals a backslash b is used so often that they put the most optimized algorithms in there for that, for solving for that system of equations. Solving the system of equations can be like half as long as actually finding the inverse if you're careful. Anyway, so we solved some system of equations, and we don't really have more in the lecture slides, but let's take a look at something here. I think we do have a homework. What do we have? Um, Lab week 6. Was there a homework 4 posted? Oh, right. That's the current one. Maybe I have a homework 4. I thought I had a homework 4. Do I not? No, I don't. Okay, well, if we don't, we don't. I thought I had posted one already, but I haven't. So what I'll do instead is I'll just find some system of equations. So system of equations example. Um, say 5 by 5. Let's do a 5 by 5. I'm sure we can find one. Oh, that's a solver. I don't want that. Give me I just want one to solve for us. An example. You're making my life so hard. Maybe if I do images. Ha 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 ha. So we'll solve this one just to see. So you can see what I was talking about, how the variables are often called x1, x2, x3, x4 rather than xyz, because this way you can have more than just one or two. So like, let's see, it says using MATLAB Simulink to design a model to solve the system of linear equations. Well, we're not doing that. We're not using Simulink. But we can solve the system of equations pretty fast, right? So if I were doing this by hand, you could just type it all at the command prompt. But sometimes what it's easier to do is to do it in a script. So if I do file new script, and the reason it's faster sometimes or easier to do it in a script is because it'll let you like set up A and B because it lets you type it all out. And then, if you made a typo, you can fix it. So if we're doing this, you type the coefficients in order, right? So starting from the first equation. So the coefficients here are 6. So you go 6. You can just leave spaces, -3, +2, +1, -1, 1, semicolon. And then you type the next row, -3, -7, 0. They were nice enough to put a 0 rather than to leave it out. That helps us type. 4, -2, 1, and we're done. 4, -3, +6, -1, 2, 1, semicolon. 6 equations, 6 unknowns. Like that's quite a bit of typing. We did 1, 2, 3. We're on the fourth one. So fourth one is 2, 4, 5, -7, -3, 2, semicolon. Then fifth row, -1, 5, -4, 0, 8, -2, semicolon. Next row, 3, 0, or 2, 5, -6. There we go. Right. So the advantage of putting it here is that I typed it once, right? And I can just save this file, save file as, and I can just call it like, let's say just system script.m, something like that. And let's see if I can put the command window somewhere. No, I can't detach it. Okay. Well, I have failed. How did the help window get up here? Window, command window, attach. Okay, that's good. All right. So like if I run my script, I can hit the play button and we can see our A there. And we can, if we made a typo, we can fix it, right? So you can double check 6, -3, 2, 1, -1, 1, just matching it up with the top row. -3, -7, 0, 4, -2, 1, right? You can just go through and make sure it's right. And so that's the advantage of using a script is to make sure that you've got it right. So once you have that all done, right, that's the A, I can go down to the next row and I can type in the B. And so the B, if you remember, is just the list of all the coefficients from the other side. So this one is 11, -5, 28, -6, +25, -4, right? So I just typed in these numbers here in a row. It needs to be a column, so I'll put an apostrophe at the end. So now if I save this and I run it, we can just double check that we typed those in right. I didn't check all of the matrix. And then to solve it, x equals a\b. Simple as that. So we can hit save, run it again, boom. So these are our answers. Now, I thought maybe that these would be set up to come out nicely. They didn't, but they are what they are. So this is the solution. You can also double check that it is the solution, which we didn't talk about previously. But remember that the original equation is like we set up the a and the b for a times x is supposed to equal b. So just to double check, you can actually do a times x and just make sure that that actually comes up to be 11, -5, 28, -6, 25, -4. So if I save this and I run it one more time, you can see that we do end up with 11, -5, 28, -6, 25, -4. That's coming from that last command, which tells you that, yeah, this actually worked. So the solution was the x values, which are right here. And this was just checking that we actually did indeed get the correct answer. And so my point here is that, MATLAB is actually very efficient at, at solving a system of equations like this. Now, you might want to type it more like this, but let's see, file save. And, you see it works okay just like that as well. So you could type it in vertically, like you can kind of line stuff up if you care to. You have to be careful, like the negatives will kind of ruin you when you're trying to like line things up. Um, oh, I didn't do the last row at all. Right. So you can do something like that to help you type it in. And it should be fine to type it in that way. Um, we can just double check that that's actually working, right? Because if I do clear, that clears all my variables. I can type clear up here. No variables, run it, and we get all our answers the same. So you can go on to, you could type your matrix on multiple lines if it helps you type it in more accurately. Cool. So anyway, that's more or less all I wanted to talk about today was just how easy it was to solve a system of linear equations using MATLAB. So hopefully this was useful. And yeah, that's it. I'll talk to you guys later. Oh, it's still